You probably think you know what weight is, right? I mean, it's just the number you see on the bathroom scale. Well, what if I told you that the feeling of weight and what weight actually is in physics are two totally different things? And understanding that difference, well, it unlocks one of the biggest ideas in science.
So let's just jump right in with this total paradox. Get this, you can be completely weightless even when gravity is yanking on you. And you can feel super heavy even when there's no gravity at all. The first time I heard that, it completely broke my brain. But stick with me, because by the end of this, that crazy statement is going to make perfect sense.
All right, so to crack this puzzle, we have to start with the basics. We need to get a really clear idea of what physicists mean when they say the word weight before we can even get into what it feels like.
Okay, so in the world of physics, weight is super specific. It's the force of gravity that a giant object, like a planet, is pulling on a smaller object, like you. The force the Earth is pulling on you with right now is your true weight. If you were on the moon, its gravitational pull would be your weight there. It's that simple.
And of course, there's a famous little formula for it. F equals mg. Here, F is the force, your weight. M is your mass. That's the amount of stuff you're actually made of, and that doesn't change no matter where you go. And G is just the strength of gravity wherever you are. Here on Earth, G is a nice steady 9.8 newtons per kilogram. So your true weight is just your mass times 9.8. Easy, right? But here is where it gets interesting. That true weight we just calculated, that's not what your bathroom scale is measuring. And it's definitely not what you feel. So let's talk about what's really happening when you step on that scale.
Seriously, take a second to think about this. You're standing on a scale. Gravity is pulling you down. But is the scale actually measuring that downward pull? Or is it measuring something else entirely? This question right here is the key to everything. And the answer is, it's measuring something else. The scale measures the force pushing up on you. Physicists call it the normal force or the support force. And we're going to call it your apparent weight. This is the whole ballgame, folks. The feeling of being heavy isn't gravity itself. It's the floor or your chair pushing back up, stopping you from falling through it. That's what you feel.
So let's put these side by side. True weight, that's gravity pulling you down. Apparent weight, that's the support force pushing you up. Now, when you're just standing still on the ground, those two forces are perfectly balanced. They're equal. That's why your scale gives you the right number. But what happens when you're not standing still?
And to really get a feel for this, we're going to head to the best physics laboratory ever, an elevator. It is the perfect place to really feel the difference between your true weight and your apparent weight. Okay, so picture it. You're standing on a bathroom scale inside an elevator. The doors close, and it suddenly accelerates upward. What happens to the number on the scale? What do you feel in your legs?
You feel heavier. The scale reading actually goes up. Think about it. To push you upwards, the floor doesn't just have to support your weight. It has to give you an extra shove to get you moving. It's pushing on you with more force than gravity is pulling down. That extra push increases the support force, which means your apparent weight goes up.
All right, let's flip it. Now you're at the top floor. The doors close, and the elevator starts accelerating down. What do you feel this time?
You feel lighter. You know that little whoosh feeling you get in your stomach? That's your apparent weight going down. Because the floor is kind of falling away from you, it doesn't need to push up on you as hard to support you. The support force gets smaller, the scale reading drops, and for a moment you feel partially weightless.
Okay, but let's take this all the way. This is just a thought experiment, so don't worry. But what if the cable snapped? What would the scale read if you, the scale, and the whole elevator were just falling?
0. The scale would read a big fat 0. Your apparent weight would be nothing. And why? Because the scale is falling at the exact same speed you are. It doesn't have to push up on you at all. There is no support force. And that is the true experience of weightlessness. Gravity is still there, pulling on you just as hard, but with nothing pushing back, you feel absolutely nothing.
Now this little observation, something you can feel in any elevator, actually had mind-blowing consequences. Because this exact line of thought is what led a young Albert Einstein to one of the most brilliant ideas in human history.
So here's Einstein's amazing insight. Imagine you're in a sealed room, no windows. Could you perform any experiment to tell the difference between being in that free-falling elevator on Earth and just floating around in deep space, millions of miles from any planet? The answer is no, you couldn't. The experience, the feeling of weightlessness, is absolutely identical.
Now, let's look at the other side of this coin, which is maybe even crazier.
Could you tell the difference between just standing still here on the surface of the Earth and being in a rocket ship in deep space that's constantly accelerating upwards at 9.8 meters per second squared? Again, the answer is no. You absolutely could not tell. In both situations, the floor would be pushing up on your feet with the exact same force, giving you the exact same sensation of weight.
This is the equivalence principle. It's the idea that, from your perspective, the effects of gravity are completely, totally, 100% indistinguishable from the effects of acceleration. There's no test you can run, no experiment you can do inside your box to tell them apart. They are, for all intents and purposes, the same thing. And that right there is the punchline. This simple idea, something that starts with feeling heavy or light in an elevator, was the seed. It's the little thought experiment that grew into one of the great pillars of physics, Einstein's general theory of relativity, which is our modern understanding of gravity itself.
So that leaves us with one last massive question to chew on. If the experience of gravity is identical to the experience of acceleration, then what is gravity, really? Einstein realized that maybe gravity isn't a force pulling you down at all. Maybe it's just what happens when massive objects bend and warp the very fabric of space and time. And that's a wild thought to leave you with. Thanks for joining me for this explainer.